So, but we went through the last few steps very quickly, I think. So especially these derivation parts for equation number 7, 8, and 9. And ultimately, we had this bigger A matrix because of the introduction of few additional steps, state variables, as well as the presence of UPSs in the excited dynamic block. So today we will start with those derivations. We'll look into those derivations and then we'll go through some simulations. Okay, and then if we have some time left, then we'll be probably going in switch into the new topic of turbine and governor modeling. Okay, so if we just quickly have a review of the steps that we went through. So there were several steps. The first step was actually to ignore any sort of damping present in the system. So that allowed us to get rid of the D value here. So D was assumed to be 0. And our first target actually in the step number 1 was to identify the frequency of oscillation for the system. So the natural frequency of oscillation, which is denoted by omega n. And with the assumption of D equals to 0, we actually got rid of D from this part of the equation. So we had the transfer function representation between the output del delta from the mechanical loop of the system and the input del PM. Then we said, well, let's take the external input del PM equals to 0. And let's see the effect on del delta, any non-initial value of del delta on the system dynamics. So that would give us the idea of omega n, because this is natural frequency of oscillation. By definition, natural frequency of oscillation means the oscillation that the system experiences without the presence of any external disturbance. Okay, that is because of its own stored energy. And that's why we took some non-zero value of del delta, but some 0 value of external input del PM. Then we solved it, and ultimately we got the solution of S. So this is second order system. So it gave us 2 roots. Both roots were complex in nature. So basically we got a complex pair of eigenvalues. And because this is nothing but S equals plus minus j omega n. So this is the omega n. That means the term that is appearing under the square root along with the square root, that would give us the omega n expression. So then this was the completion of step number 1. In step number 2, we tried to identify what's the phase lag in the electrical loop because of the introduction of the exciter block. So that phase lag was basically coming through the starting from the summing junction at the exciter block. So this is the summing junction. So we're looking at the lag, presence of lag between this UPSS and between this del EQ dash. So basically this was a closed loop with a negative feedback from this point through K6, and we had 2 forward transfer blocks, transfer function blocks. So we calculated it and we evaluated the lag actually at this frequency, at the frequency of natural frequency of oscillation, that is omega n. So when we did that, we said that, well, we would find some magnitude of that transfer function that we denoted by GEX, EX for the exciter, the magnitude of that and the angle of that. So we were interested specifically with that angle gamma. And there was a conclusion actually, this is a thumb rule, but this may also, you may also take it like 30 degree to 45 degree. Okay. It's like something like an iterative technique, you could say at this point. Well, you can take, let's say, a 60 degree value for one stage, you design it, and let's say you check whether the design is okay or not with you. Does it satisfy the design criteria or design consideration or design targets? If not, then let's say you choose a reduced value of gamma for one stage. Let's say you make it 45 degrees for one stage and redesign it. Okay, from here onwards, redesign it. And let's see whether the response that you have got, whether it satisfies your requirements or not. So in this manner, you don't have to be actually very rigid with this 60-degree, but you can relax it a little bit, but in the lower direction, not in the upward direction. That means not beyond 60-degree, but maybe between 30-degree and 60-degree, you should be safe. And you can play with the value a little bit to satisfy your design criteria. So at this point, you choose how many steps you would need actually. How many stages of PSS blocks or lead blocks you would need in your PSS. So after that decision, you move forward to step number 3, where you choose a pattern for your PSS, that is GC, that is the G compensator. So that is 1 plus ST1 divided by 1 plus ST2. This is the lead leg block, generic representation for any lead leg block. And N represents the number of stages, how many stages you are actually looking for. And the target is to completely wipe out the phase lag produced at the transfer function GEX. So whatever lead you are going to design through GC, that should wipe out the GEX lag, that is gamma. This is basically gamma. So this is gamma, and this is your angle of GC, should be 0. So at this point, actually, we are taking care of the angle, but of course, it has a certain magnitude. So take care of that magnitude. Actually, we go to the fourth step, where we take into consideration of the magnitude issue of GEX. And accordingly, we generate some gain block. We design some gain block to cater for the magnitude issue. So here are the steps. We already took the steps. So here, that is basically the continuation of step 3, where we actually come out with the value of T1. Okay, and we assume some value of T2, reasonable value of T2, and we say that rule of thumb is take some value from 0.02 to 0.15 seconds. And then we come out with the value of T1, and then with those values known, T1 and T2 and also omega n, we go for step number 4, where we look for some desired damping. We look for some desired damping ratio zeta desired. And now here, actually at this step, we only consider the gains of the blocks. Okay, so you consider the gain, GEX, gain of GEX, you consider gain of GC. So at step number 4, we are only dealing with the gains, whereas in step number 3, we are only dealing with the phase angles of the transfer function blocks. There are 2 basically, GC and GEX, which are under consideration. So then after these steps are done, intermediate steps are done, you come out with the value of KPSS. So that completes the design. Of course, you are left with some value of the washout blocks, time constant for the washout blocks. And again, it takes some reasonably large value between 5 and 10 seconds. Large, of course, with respect to or compared to these values of T2 and T1. Okay, you see the time constant associated with the compensator block are pretty small. T1 and T2, both of them. Of course, we haven't calculated T1 yet, but when we will calculate, we'll see that the value is not that high, not as high as the TW time constant. So thus it is considered as pretty large compared to the compensator time constants. So the washout time constant should be large, let's say 5 to 10 times than T1 approximately to serve our purpose. And that completes the design process. And then we said that we will have some updates in the state equations, and of course, some new state equations. And then we said that this would be the final A or system A matrix after incorporation of the some updates in the state equation, specifically the state equation associated with the excited dynamics, and there will be two more state equations. So the system order would be increased by 2. So it was previously 4, fourth order system with the inclusion of exciter. At the very beginning, it was third order, where we considered only the flux decay model. So the system matrix was 3 by 3. Then we introduced the exciter block, a simplified exciter block, of course. If we take a detailed exciter block, then of course, you will have a few more state variables associated with the exciter itself. Again, the generator model is a little bit simplified. Okay, it's not exactly the classical second order model, but it is simplified because it can go up to 8th order. The generator model itself can go up to 8th order, but we are taking, for this course, we are taking only third order model. Then the exciter is a single ODE, first order ODE, so it becomes fourth order model. Then with the UPSS, single stage UPSS, it becomes sixth order model. Okay, and there are two inputs. One is the mechanical input or deviation in mechanical input, and another one is deviation in the voltage reference set point in the exciter block. So let's see now how can we actually get these. So let's take a whiteboard. Okay, and let's try to number the equations. So we had del delta equals omega base or omega naught, whatever, del omega. Then we had del omega. These are the equations that we already have. 1 upon twice h del pm minus del pe. Of course, del pe is nothing but k1 del delta plus k2 del eq prime. We are not actually considering any p damping. Okay, so there is no d del omega. That is ignored for the design purpose. For the design purpose of PSS. And then we have del eq dash, and this is 1 upon TDO prime delta EFD minus K3 del eq prime minus K4 del delta. So these were the equations up to the third order. And then we said we have an exciter. And now this exciter has some additional input in the form of UPSS. So this is basically the output of your PSS. Here you have del VREF, and here you have, so this is plus, and this is minus del VT. And del VT is nothing but K5 del delta plus K6 del EQ dash. And then we have this block, the exciter or the AVR block, Ka over 1 plus STA. And that would give us delta EFD. So this is the updated block with the incorporation of UPSS. So now we have to simplify this block and try to find out delta EFD dot from here. So if we do that, then what do you get? Let's see. Let's try to do it here. So, so we have output from this block is delta EFD, and input is del VREF plus UPSS minus delta VT. And that is Ka over 1 plus STA. Then if we continue, we will get delta EFD plus TA. Then basically we are cross multiplying this one. So we have TA into delta EFD dot, and that is your Ka into del VREF plus UPSS minus K5 del delta minus K6 del EQ dash, which is nothing but your del VT over here. Then we actually need only delta EFD dot on the left hand side. So this would be Ka over Ta del Vref plus UPSS minus K5 del delta minus K6 del EQ dash minus 1 by Ta delta EFD. So this would be the updated equation. So you can clearly see that before in the previous derivation, that means before we designed the PSS, we didn't actually consider this presence of UPSS. We considered it to be 0. But now it has this delta EFD dot equation. It has the additional entry of UPSS, and the coefficient of that is simply Ka over Ta. So that means if we now go here, so you see now equation number 7, this is what I tried to derive. So here is the presence of UPSS, and this is the K over T, and this is the remaining part of the equation. So this is how you can get the derivation done for equation number 7. Of course, with the incorporation of PSS, and now your exciter dynamics is a little bit modified with the presence of UPSS. So once that is done, now let's go back to the derivation part and let's continue with the remaining 2 state equations. Let's try to derive them. So this is done. Now, so we can erase it. And probably there are no changes there actually. So just leave them there, just erase them. Okay, so next we have to take the, let's take the first block for the PSS. So PSS in the first block, it was a washout block, and this was the transfer function 1 STW divided by 1 plus STW, and the output here was taken as some intermediate state variable U1. So if we simplify it, what we would get, U1 divided by del omega is simply STW divided by 1 plus STW. S is here again the Laplace operator. So then we cross multiply, so it would become U1 dot to TW, and here del omega dot to TW. So then we would take U1W, so U1 dot del omega TW minus U1 into 1 upon TW. So this is what we will get. Now the problem is that on the right hand side we have a presence of another derivative of state variable del omega dot, but luckily we know what is the expression of del omega dot. I have erased it, so let me rewrite it here. So this is 1 upon twice H del PM minus K1 del delta minus K2 del EQ prime, of course without the damping. So simply we have to plug in this expression here. So it would be 1 by twice H. You can simply write TW by twice H delta PM minus K1 del delta minus K2 del EQ dash. So this completes this part. Then minus U1, and then so this is the equation that you will get for U1 dot. Okay. So it's again this PM, this del PM is nothing but your input, one of the inputs, disturbance inputs, of course, not the control input. And this is how you can get the equation, state equation for U1 dot. Now, if we compare it, so here it goes. Of course, del PM is not included here, but of course, del PM would be there. Okay. So if you want to incorporate del PM, then you have to include it here. But probably here I consider del PM equal to 0 still, but in general, it is non-zero. So there will be some input for del PM. And the remaining part is K1 by twice H. So if we take both the whiteboard. Okay. So if we just try to minimize this a little bit, just for comparison. Yeah. So let's minimize this. Yeah. So this is minus K1 by twice H. So if you compare it, minus K1 by twice H del delta. So this is minus K1 by twice H, and this TW and TW would be cancelled. Actually, the part TW won't appear for any of these three. It will only appear for this one. So 1 by TW would be multiplied with this. So you will only have minus U1 by TW. But for the first three parts, there won't be any TW there or there in the denominator. So you see minus K1 by twice H. This is the first part, minus K1 by twice H here. Then minus K2 by twice H del EQ dash. This is minus K2 by twice H del EQ dash, and then minus U1 by TW. And of course, you have del PM by twice H in addition to all these three. So you can write plus del PM by twice H here. Okay. So then the last part. So if we simplify this, it would be simply minus K1 by twice H del delta minus K2 by twice H del EQ dash minus U1 by TW plus 1 by twice H into del PM. So this would be the change. Okay. So now that we have it, so you already have the additional state equation derived in the form of U1 dot. Now let's go and look into U2 dot. Okay. So for the U2 dot block, we have the second and the third block there. The second block is the lead block. Of course, we are considering one stage PSS here. So now this U1 is the input. We have 1 plus ST1 divided by 1 plus ST2. And then we have a KPSS, of course. So you can multiply the KPSS here, the same thing. So you can simply multiply KPSS under the same block, because simply again, there is no integrator or differentiator. There is no S there with KPSS, simple gain. And this would give us UPSS. So again, you do the same, following the same process. You take the transfer function first, 1 plus ST1 divided by 1 plus ST2 multiplied by KPSS. Then you cross multiply. So it would be UPSS plus UPSS dot T2, then KPSS to U1 plus U1 dot T1. Then UPSS dot would be KPSS U1 plus KPSS T1 U1 dot minus UPSS whole divided by T2. Again, you can see there is U1 dot, but again, luckily we have the U1 dot already derived. So this whole thing would be plugged in here. Okay, I'm not going to do that part. It will take some space as well. It will take some time. But of course, you know what to do next. Okay, so you have to just plug in the value, plug in the expression of u1 dot, the whole expression here. And again, probably in my PDF file, I ignored 1 upon twice h into del PM, but that you can consider it there. Okay, if you are putting some, including some disturbance in del PM, then of course it should be there. If you are including some disturbance in del Vref, then you can drop it out. Okay, you can drop it because you are not considering del PM. But it is safe to keep all these variables to make the expressions generic in type, so that you can incorporate any value there. If it is 0, no problem, you can keep it 0. If it is non-zero, then you are there. Okay, you can incorporate it pretty easily in your system matrix, the effect. So this is how you can get the expression of UPSS dot. So this is your 5th state equation, and this is your 6th state equation. And before that, we showed how the delta EFD dot, that equation would be a little bit updated or modified with the incorporation of UPSS. And this UPSS will, of course, go to the summing junction. Okay, this is the closed loop. This is the summing junction minus del VT, and this is plus del Vref. And this is the exciter. So this is how, so this is your Ka over 1 plus STA. And this would be your delta EFD. So this is how it would actually come back to your exciter block, the UPSS. Okay, any question? No question. Okay, so let's proceed. So this is where we should be able, after the derivation of these state equations, we should be now able to deal with the building up of this big A matrix. And of course, this is X dot, this is A, this is X dot, this is your A, this is X. Again, of course, there should be some changes because this del PM, presence of del PM was found in 2 more places. Okay, one in the expression of U1 dot and another one in the expression of UPSS dot. So in your 5th entry here and in the 6th entry here, you should get something non-zero. Okay, because there is some delta PM here, and similarly, because this is U1 dot and U1 dot was appearing in the expression of UPSS dot, so this del PM will also carry over here, of course, with some probably some coefficients multiplied with that. So accordingly, these entries are to be updated here if you are considering non-zero del PM. Okay, so this is the single stage PSS, and similarly, you can continue the design process for the 2-stage PSS. I already mentioned it in the last class, but let me repeat it a little bit again. So if we go for the 2-stage PSS, of course, the number of states would be increased. It would not remain the same as this 1-stage PSS design. However, the calculation of omega n, the calculation of gamma, the calculation of KPSS, the T delta, T omega, all these would be identical to the 1-stage PSS. So that is a plus. However, the calculation of the T1, the modified excited dynamics, that is expression of delta EFD and other updated state equations, and the formation of A matrix are discussed here next. So the form of the compensator would be now like this. So you will have 2 blocks and they will appear in series, in cascade. So you can multiply them. So basically you have 2 blocks here, 2 stages here. This is first stage, and then this is the second stage. So you will have del omega being fed to your washout block, STW over 1 plus STW. And then this we consider it as U1. Then you have the first lead block 1 plus ST1 divided by 1 plus ST2. So maybe you can take it as U2, and then 1 plus ST3 over 1 plus ST4. Then you have the gain block KPSS, and ultimately you will have the UPSS. We are not considering again any state variables here because this KPSS is simply a gain block and it is not introducing any new state variable. So we are directly taking the state variable here. So no state variable should be here. Like this one, we have a state variable because we have some S operator within the block. So that introduces some state variables. So this would be the configuration for your two-stage PSS here. And to make the design identical to the one-stage block, what you can simply do, you can simply assign T1 equals to T3. So what you are doing, you are simply taking T1 and you are saying that should be exactly equal to T3. You are taking some value of T2 and you're saying that should be exactly equal to T4. So as we saw earlier, the T2 are actually assumed. The value of T2 is actually assumed within a certain range. So that is assumed value. And once you assume it, you assign it to T4. So that part is done. So the design part involves actually the calculation of T1. And once you get T1, you assign it to T3. And you simply go with the simplification steps. Simplification of these blocks, transfer function blocks. That means you again go for U1 by del omega. It is STW over 1 plus STW. And you calculate what is your U1 dot and so on. Okay. So in the two-stage PSS, in addition to U1 dot, you will have some U2 dot because we said it here. And of course, you will have UPSS dot. So that means you will have one additional state here compared to one-stage PSS design. So, and in between, you have to calculate the T1, of course. So in calculating T1, what you would do, because T1 is only associated with one of the lead blocks. Okay, so, and you have to compensate the phase lag gamma that is produced by GEX. This is the total phase lag. You have to compensate this block with the help of two blocks, which are appearing in cascade form. So this is the cascade or the series form in your block diagram representation. So because you are only designing T1, you have to take the gain, half of the gain, okay, not the full, sorry, half of the lag produced by GEX, not the full lag, okay, because you are designing for T1 and you are assigning it to T3. So that means if you can design for half of the gain for one block, then if one of the block is enough to give you the proper lead, then the remaining block should be able to get rid of the remaining lag. Okay, so that means if your total lag is, let's say, 80 degrees, gamma is 80 degrees, you are designing for T1, that is one of the blocks. So you should design it like this block should take care of 40 degrees and this block should take care of the remaining 40 degrees. This is what I mean. So if total gamma is 80 degrees, and that is actually the angle of GEX. So if you are designing T1, then simply you are designing for one block. That means you have to plan for 40-degree compensation. So that means you have to go for this. T1 should be designed for gamma by 2. So this is what is done. So the T1 should be giving you compensation, lead compensation for the GC would be provided by the T1 or this block. That will come from GC, and that would actually cater for GEX over 2 or gamma over 2. Okay. That means, for example, here 40 degrees, not 80 degrees. So you shouldn't take full 80 degrees here because you're only designing for one block, T1. And then you will be assigning it to T3. And the remaining part is actually the same as we did. Simply you have to take gamma over 2, then GC is, this is the representation of GC, that is 1 plus ST1 divided by 1 plus ST2, evaluated at S equals to j omega n. They should sum up to 0. This is for cancelling the phase lag. And then you simplify the expression. And this is how you actually go. Okay, these are the same steps as we did earlier. So there is nothing special. And then once you get T1, you assign it to T3. And once you get the calculation done, as I said already earlier here, that the design of PSS is the same. So you don't have to bother too much about that. Of course, the expression of GC has to be this one. Okay. In the derivation of KPSS, the expression of GC has to be this one. But because we are not mentioning the whole thing there, we are only saying we have to have, if you look at the KPSS design part, you see we're not explicitly expressing GC. We are simply saying GC magnitude at S equals to j omega n. So in that way, the design process for KPSS are actually identical. We are not going into the expression. We are simply using the expression of GC. So if that is done, then you can simply calculate KPSS. Again, take TW equals to any value between 5 to 10 seconds, comparatively larger than the time constants associated with your compensator blocks, that is T1 up to T4, whatever values you are using. At this point, you would know what is T1 up to T4. So then you take TW accordingly, let's say 5 times of T1 or something like that. Then with the incorporation of two-stage PSS, again, you have the updated expression for delta EFD dot. Again, this is U1 dot, this is U2 dot, and this is UPSS dot. And these are the corresponding simplified entries here. Okay, I have just used some simplified expressions, and later on I have explained what is inside those expressions, just to save some space. Okay. So after these, again, considering D equals to 0, like in the previous case, and this is the updated state space model with the two-stage PSS. And once you do that, you plug in the entries, and now you have a 7th order system, 1, 2, 3, 4, 5, 6, 7. And these last 3 are associated with your PSS. Because it is a two-stage PSS, there would be 3 state variables. And again, if you want del PM to be non-zero, you have to incorporate the corresponding entries here. So this shouldn't be 0. Okay, if you are considering del PM disturbance. However, for del VREF, it is fine. You are done. Okay, so then let's go. Okay, so this part is done. So now we should go to the simulation part, and we will see how we can do that. So let's run MATLAB first. Take some time to load. Okay. So any question till now? Okay, no question. So let's wait a little bit till MATLAB loads. So now we have the MATLAB environment opened in front of us. So let's go to the design process for the PSS. Is it visible, the MATLAB window?
Yes, sir.
Okay. So here I have taken a data set from the book of Sauer and Pai. Okay, it is not exactly the same data set that we used for the earlier demonstrations. So a little bit updated, just to cross check whether the results are matched with the results obtained by the author of the book, SOR and Pi. So, and this is example 8.7 from that book. Okay. So these are the data. So you have H, the inertia constant is 3.2, the TDO dash is 9.6 second, XD, XQ, XD dash are not exactly the same that we used before. But all the data that are required are, the data requirement is same, but the values of the data are probably a little different. And omega base is again 2 pi f. This is the transmission line reactance. This is the base frequency in hertz. This is the base angular frequency 2 pi f. Okay, now it's a little different. So this is another reason why I have taken it, because the operating point data is not exactly same. Okay, if you look at the previous one, probably, is it available? Yeah. So if you look at this one, the operating point data given was actually this VT. So we had actually VT, PT, the power transferred by the generator, real power transferred by the generator, reactive power transferred by the generator, QT, and the magnitude of the terminal voltage of the generator. So this was the operating point under consideration. Okay, so this was the values for the operating point available. However, in this example, it is a little bit different than that one. Here what we have actually VTM. That means the magnitude of the terminal voltage for the generator and the magnitude of the infinite bus voltage. Okay, so these only you are given with some magnitudes and a angle of the terminal voltage, phase angle of the terminal voltage. Okay, so that means if I draw the network now, I don't have the information of P and Q anymore. So this is your XT. This is your infinite bus. So this is the network. This is your VB. And about VB, we know only the magnitude. But of course, we know that VB should be the reference phasor. So the phasor VB should be 1.05 angle 0. So this information can easily be extracted from this one. You don't have any PT and QT value available here, but instead you have the value of VTM. This is this, and that is 1.0. And of course you have theta VT, that is actually VT is represented by VT angle theta T, and that is 15 degree. Okay, that is 15 degree given in the problem statement. So this is basically 1.0 angle 15 degree. So instead of PT and QT, you have this set of information available. So how to start the calculation process and how to get the phasor diagram done. So can you solve this? I mean, what should be I now?
VT minus VB.
So phasor VT, phasor VB divided by
XT.
Something missing.
JXT.
JXT. So J was missing. Basically, you have a J here, which I didn't mention, and this is something like Z. Okay, so it should be read as Z equals JXT. So you should be very careful about using this J. The generic representation should be RT plus JXT. Okay, so RT is not there, ignored, but J cannot be ignored. So please use this J. I didn't use it here, but it has to be used. So this is what is done here in line number 11. Okay, IT equals VT minus VB divided by JXT. So VT is taken as a phasor representation, VTM exponential J theta VT. Again, VB is taken as a phasor representation, VBM, that's the magnitude multiplied by exponential of J, and the reference angle is 0 here. Then you have IT. So this is your IT. Okay, once you have IT, then you can calculate EQ equals VT plus, of course, phasor JXQ IT. And we discussed it elaborately why we can use it and how we can use this for the initial value calculation part. So the angle of this is basically the delta. Remember, we are taking VB as the zero reference angle directly here. Okay. So this is VB. If this is VB, if this is EQ, so that should be your Q axis. This should be your delta, and intermediate, there should be some VT. So this is the phasor representation, and IT would be lagging to VT by some angle. Okay, IT would be lagging. So the angle of IT is basically denoted by theta IT, that is angle of IT. Let's say somewhere here, or depending on the value, it would be somewhere there or there or there. It depends on the given values. So you have got the value of IT. From there you can calculate the angle of IT by this expression. You can calculate EQ and the angle of, you can calculate the phasor EQ, and that phasor EQ would be along the Q axis. So this is the direction of Q axis. Once you get the Q axis, then 90 degree out of that should be your D axis. Okay. So once you get Q axis and D axis, then the remaining job is pretty easy. Q and D are drawn. So then you can calculate VTD for VT phasor, VTQ, VTD, VBQ, VBD. If this is your IT, let's say, then ITQ and ITD and so on. So those parts are taken care of here, okay, in these 4 lines: VQ and VD, IQ and ID. And then you have EQ prime. This is your third state, EQ prime or EQ dash. And this is VQ plus XD dash ID. Plus XD prime ID. So this is done here in line number 19. Once that is done, so you also know the initial value for EQ dash, the third state variable. And then you can also calculate VBQ, the Q component of the VB phasor, and VBD, the D component of the VB phasor. And then you can calculate the actual PT that is available in your network, because this value is not given explicitly. So line number 22, at line number 22, once you have these VQ, VD, IQ, and ID, then you can use this expression of PT, that is VD-ID plus VQ-IQ, which was derived earlier before mid. So once you get PT, because there are no resistive element present in your network, so you can clearly say that this is your same as the mechanical power. So P, you can equate PT equals to PM. You set your initial value of omega to 1. Then you also calculate the initial value for your fourth state variable, that is EFD. Actually, it is delta EFD, but you also need EFD, not EFD, okay, during your calculation further. So EFD is dependent on EQ prime and ID. And this is the relation presented in line number 25. So you have got the numeric value for EFD. Then the remaining part is for linearization. You formulate C1, C2, and C3. Again, you formulate P1, P2, P3. Then you formulate the K constants, K3 and K4, K1 and K2. Okay, now you are in a position, once you have got the values for K1 up to K4, you are in a position to calculate the third order system matrix A. I have denoted it by A underscore third in line number 45. So once you build it, then you should be able to find out what is the eigenvalues here. So let's run it. Let's run it and see how much, or what's the eigenvalue. So we can see that in that example for the Sauer and Pi book, that is 8.7 example. Well, the third order system is stable. However, the among the three, one pair, there is one pair which is complex conjugate, and there is another real root with a real eigenvalue, which is pretty close to your y-axis, but still it is negative. So we can call it as a stable system for the operating point under consideration. By operating point, again, I mean these three values, okay? Magnitude of Vt, magnitude of Vb, and the theta. You can clearly check that if you change any of these, Vt, Vb, or theta Vt, of course, your eigenvalues would be affected, okay? So let's just check it. Just for checking purpose, let's make it 1.15, just for an example. And let's rerun it and check it. So you see now the scenario is changed. Well, regarding stability, the scenario is same. The system is still stable, but it is the complex pair of eigenvalue which has moved nearer to the y-axis, and the real part of the eigenvalue, real of the real eigenvalue, the third one here, this is actually moving away from the y-axis. Okay, so with the change in the operating point, basically your stability scenario, the dominant eigenvalues, all the things are greatly affected. So that's why the analysis, the small disturbance analysis, is pretty much, linked with your selection of operating point. If you change the operating point, then you have to go through all these steps, and you have to check whether in your third order system, before incorporating the exciter, whether your system is unstable or unstable, or what are the conditions of the eigenvalues, which are the dominant eigenvalues, and so on. So let's take it back to where it was. So then again, it is the same value as we started with. So let's continue. So then we make the calculation for formulation of K5 and K6. So the K5 and K6 are calculated. Then we take the value as mentioned in that example. Ka, the gain of the AVR is 400. The time constant of the AVR is 0.2. Now we are in a position to formulate the fourth order A matrix. So this is the fourth order A matrix. And now what we do actually, as I said, this is not required just to know about the stability. Okay, just to know the stability, we can simply adopt our this command, okay, eig third. But this, I have actually built a small function that would give us actually the participation factor idea. How would it help? Let us see. What additional information can it bring to us? And very critical information. So the participation factor is nothing, but it actually relates, for example, what is the necessity? Let's go back again and check here. Again, let's check the third order eigenvalue. Okay, so you have three eigenvalues, right? What are the states associated with the third order system? We have del delta, we have del omega, and we have del eq dash, right? And what are the eigenvalues? The eigenvalues are this: minus 0.1374, minus 0.1374, minus minus 0.1374, plus minus j, that is I here actually, I or j the same, these are complex, j 7.3680. So minus 0.1374 plus minus j, how much is it? 7.3680. And the third eigenvalue is minus 0.0764. So we have three eigenvalues, where one is a complex pair, the first two, and the third one is simply a real eigenvalue, real root. Now, can we tell which of the eigenvalues is associated with which of the state? Just by looking at this list, that these are the states and these are the eigenvalues. So just at this point, just with this information, we are not able to link the eigenvalues with the states. Okay, we don't know which eigenvalue belongs to which state. Okay, why this information is so vital? This information is vital actually in designing controllers. Okay, let's say among these three, which of the eigenvalue is the closest to the y-axis? The third one. Okay, because this is the negative. Look at the negative real part. This is minus 0.13. So probably this is somewhere here. Minus 0.1374 plus minus j. So this is a complex pair. But this one, you see, minus 0.07. So the distance from the y-axis is almost half. So this is lying here. So this is the dominant eigenvalue. This is nearest to the y-axis in the S-plane. So to improve the stability of the system, this is stable, no problem with that. But if we want to improve the stability of this system, then we have to identify which of the state is actually, or which of the state has a tendency to create trouble regarding stability, or which of the state is more prone towards instability. Okay, so in the current scenario, this third eigenvalue is nearer to y-axis. So this is the critical eigenvalue or dominant eigenvalue. If you want to design some controller, then you have to ensure that this eigenvalue is shifted more towards the left. So for designing the controller, before designing the controller, you have to identify the physical variable associated with this eigenvalue. In practice, which state is linked, or which parameter of the system, which variable of the system, which information of the system is required, so that you can clearly design a controller to shift the associated state, to shift the physical variable from here towards the left, so that your system becomes more stable or less prone to instability. Okay. So for that, you have to actually identify which of the state is linked more with this eigenvalue. Is it del delta? Is it del EQ prime? Or is it del omega? The participation factor actually helps us to understand that phenomena, or to understand that relation. Okay, participation factor. And that is nothing but you just calculate the eigenvectors. You just calculate the eigenvectors for your A matrix. And there are actually two of them. One is left and one is right. If I simply say eigenvector, it refers to right eigenvector. So mathematically, what is an eigenvector? Simply the mathematical definition I'm giving you here. So it is, if your system matrix is A, or if it is, let's say, A third or A fourth, whatever. So simply I'm using A, then multiplied by, generally it is denoted by V vector. Then this eigenvector should satisfy, for this A matrix, this eigenvector should satisfy this relation. Okay. Because it is appearing on the right of the system matrix, for satisfying this equation, this is known as the right eigenvector. Okay, right eigenvector, because its presence is on the right of A. Whereas the left eigenvector, denoted by W, appears on the left. And then this side remains as it is. So this is left eigenvector. So if you know your A matrix, you know the eigenvalues. Lambda is nothing but scalars, which are eigenvalues. Okay, lambda is not a vector, lambda is a scalar. So if these conditions are satisfied, for the right eigenvector, this condition has to be satisfied. For the left eigenvector, this condition has to be satisfied. Then you can calculate the lambda, the V, and the W. If you know these three, if you can calculate for a certain A matrix, then the participation factor is simply depending on V and W. So that is, you take the elements of W and you take the elements of V, and then you take the absolute value of that. So that should be element wise multiplication. I'm using the MATLAB command, element wise multiplication. So W dot product into V, these are the vectors, and that should give you the participation factor idea. Participation factor. Now how that would help, let's see how this value would help. So this job is actually done inside these code. That is the function that I actually took help from net, and then I built my one. So this is where you can get the participation factor, and once you get that, it would actually it would be really helpful in identifying the relation between the states or the participation of states or in certain eigenvalue. So let's see. It is not done for the third order system, but it could also be done here. So if we continue up to this point, then okay. So then let's see participation factor. This is the fourth order. So this is a 4x4 matrix, and that is being built here after the incorporation of exciter. These are the eigenvalues. So you have 4 eigenvalues. Now you have 2 complex pairs. Okay, so there are 4 eigenvalues, but again you have all the real parts negative. Which one or which set should be dominant eigenvalue from this list? Which complex set should be dominant or critical eigenvalue?
So minus 0.0871.
Yes, excellent. So minus 0.0871, because they are nearer to the y-axis in the S-plane. But we only know this, but still we don't know actually with which state that pair of complex eigenvalue is linked up more. Okay, so now we look into the participation. So if we want to calculate the participation P factor, this would be the list. Okay, so now if you go through the list, you see these values are small. Okay, 0.0414, 0.0414 is small compared to the last two, right? 0.5219, 0.4219. Similar thing can be observed in the second one. Actually, they look identical. They look identical. Okay, the second one is the same, 0.0414, second column, 0.0414, 0.0414, 0.5219, 0.4998. They look identical. Let's make it available here so that we can read out. Okay, so now it is pretty clear. So this is your PFAC, and let's try to get the EIGV so that it becomes clearer. Okay, now the information is available. So the first and second eigenvalue, they have less participation. So along this line, you can assume, if I draw a line now, if I try to draw the participation matrix. So along this line, you have the eigenvalues. the states, and along this line, you have the eigenvalues or states. So if I go through now, this first one gives you the participation of the first eigenvalue in the 4 states. So what are the states? 4 states, first state is delta, second state is omega, third state is EQ dash, fourth state is EFD. Of course, the incremental value of all of the del, delta, del, omega, I'm just skipping those del terms. This is your first eigenvalue. This is, I mean, this line belongs to the first eigenvalue. This line belongs to the second eigenvalue. This line, the third eigenvalue. And this line, the fourth eigenvalue. So you see there is a link. So how much link is there between the first state and the first eigenvalue? This value denotes that. So it's pretty low, okay? Loosely coupled. Low participation of delta in the first eigenvalue, or low participation of first eigenvalue in the state delta, whatever you say. Similarly, the second eigenvalue, small participation in del delta. Okay. Third eigenvalue, it has the most participation in del delta. That is this. And fourth eigenvalue, it is also pretty high compared to these two. So fourth eigenvalue also has some participation, some significant participation from delta. So delta wins here and delta also wins here. But here delta is not the winner. Let's go to second one. Omega. So the first eigenvalue, omega is not there. So this is for omega. The first eigenvalue, omega, is low participation, only 0.04. Second one, omega is low participation, but third and fourth, omega is largely participating. Okay. So that means delta and omega, we have got 2 states and 2 eigenvalues. That means these two are related here, mostly participating. These 2 states are mostly participating in these 2 eigenvalues. That means this pair of eigenvalue are largely coupled with delta and omega states. So the dominant eigenvalues are identified. Okay, these are the dominant eigenvalues because they are nearer to the y-axis. So that means if I want to design control, I have to look for any error in delta variable or omega variable, and then I have to feed that error to the controller. That should take care of any deviation of delta value and omega value. Okay. About third and fourth, you see the first eigenvalue, you see EQ dash. Okay, there is a very large contribution. Similarly, second eigenvalue in EQ dash. So these two are EQ dash, EQ dash, EQ dash, and the third and fourth eigenvalue, they are not contributing that much to EQ dash. Okay. About the fourth one, same. First and second eigenvalue, EFD are largely there. Third and fourth, EFD is not that much available. So that means this pair, this upper pair, is coupled with these two. Have you got the idea how the participation factor might help us? Any question?
Sir,
Yes.
for each eigenvalue, the value for delta, omega, EQ prime, and EFD, the addition of this value should be 1, right?
Yeah, that is known as normalized participation factor. If you normalize it to 1, then that would be true, but not always.
But for third eigenvalue, sir, the addition of so it's becoming more than 1, like 0.5.
Yeah. As I said, if you normalize it to 1, if in your calculation you incorporate the normalized participation factor, I haven't done it. Okay, or from the code that I have taken from, they haven't done it. But just by simple manipulation, okay, just by a little bit of manipulation, you can make sure that all the participation, if you add them, this column should give you 1. This column should give you 1, this column should give you 1, and this column should give you 1. Okay. So that is for some specific normalizing scenario. I mean, if you can do it, that's fine. But just for giving you an idea how participation factor might help you, that is okay. Okay. Whatever calculation is shown here, that is fine. But the one that you are telling, that is further, I mean, finer than this. There is no doubt that is finer than this. If you can normalize them, if you can add them up to 1, there are two ways of normalizing. One way is to make the summation equals to 1. So that means you are getting actual weightage. Okay. Out of 100%, let's say if the summation is 1, that means out of 100%, which one is participating, how much percentage? You can easily calculate in percentage if you do that normalization, but that's not necessary. Okay, that's not mandatory. But if you can do that, it is fine. No problem with that. Any other question? No question. Okay, so if no more question, then once you get the participation factor idea, so you can see that delta and omega states, they are actually low damping. Okay, they have low damping. How do you calculate the damping? How do you calculate the damping ratio? So this is nothing but actually your sigma. All these are nothing but sigma plus minus j omega. Your damping ratio would be zeta, and the formula is minus sigma divided by sigma square plus omega square. So that would give you the zeta value for each of the eigenvalues here. So that means for the first one, it would be minus of this. So it would be plus 2.5885 at the top. And at the bottom, you should be square root, then 2.5885 squared plus 8.5020 squared. Then you will get zeta for this one. Same zeta would be available here. And then same zeta for these two. So you will see once you calculate this, you will see that the zeta value here for the lower two eigenvalues would be pretty small compared to these two. So that those are lowly damped because the damping ratio is pretty small. Then we go through the steps of the calculation of your omega n. So these are the steps associated with the PSS design. I'm not going through all the design steps because these are detailed discussed in the theory part. So once you do the coding part, that okay, here we have taken zeta desired equals to 0.3. Once you do the coding part, you incorporate your APSS, you form your APSS. APSS means now there is a single stage PSS, and this is A matrix with PSS incorporated. So how many state variables? Let's see. Here I have calculated the damping ratio. So let's run it up to this point. So that's done. Now you see it is a 6 by 6 because with one stage PSS, your system matrix size would be increased by 2. So it was 4 by 4 with exciter only. Now with PSS, it has become 6 by 6. So you see the participation matrix is also updated. Let's check the eigenvalues. Nice. So you see that we don't have any eigenvalues with less than 0.2. Okay, with less than minus 0.2. So that is the lowest. But what about delta and omega? Delta and omega was our main concern. So for that, we have to find out what is the minimum damping ratio. Okay, let's look at that. So minimum damping ratio is 0.0763. But now what about the what about the damping ratio that we desired for? Our desired damping ratio was 0.3. So the damping we have got closest is actually 0.2339. And if you look at the participation factor, what is the eigenvalue number here? So it is 1, 2, 3, 4, 5, fourth and fifth. So fourth and fifth eigenvalue should be associated with delta and omega. Okay, that was our target. With the PSS design, that was our target to improve the damping for delta and omega. So let's check that. So if you go to fourth and fifth, so you can clearly see, let me again bring it here, otherwise it would tends to go out. Okay, so okay, now you see that for the fourth and fifth column, come to fourth and fifth column, you see the fourth and fifth column, if you go down the list, The maximum that is participating is state number 1 and state number 2. Okay, that is delta and omega. So that means you have improved the damping of delta and omega states. It was pretty low before incorporation of PSS. Now, with this incorporation of PSS, it has become 0.2339, approximately 0.23. Okay, and of course, you can run the simulation, remaining simulation, time domain simulation, and you can check the responses. Okay. Any question? Oh, my time is up. Okay. 5 minutes. Any question? No question. Okay, then. So what we have done today, we have designed PSS with the steps that we discussed. And we have seen actually the application of participation factor in identifying the participation of eigenvalues in different states or vice versa, whatever you say. I mean, they are linked, how much they are linked, any states and any eigenvalue, how much they are participating in each other. In other words, they are also called mood. Okay, sometimes you will find these term moods. So these eigenvalues are also known as moods. In some literature, you will find that the moods are in mechanical domain, probably they use it more, but in electrical domain, probably they are satisfied with eigenvalues. In mechanical domain, in vibration dynamics or any other kind of dynamic study, they probably use the term moods, M-O-D-E-S, moods. And associated another term is mood shapes. Okay, so moods and mood shapes, they come together, and they are also linked with this same participation factor, because the mood and mood shapes are again related with the eigenvalues and eigenvectors. Anything is special. Okay, then if you don't have any question, then we will quit here, and inshallah in the next class we will switch our discussion to the new topic, a relatively new topic, that is on the modeling of turbine, and then we will go on to the modeling of governor dynamics. So what the modeling of turbine will allow us, it will actually allow us to get this delta PM, okay, get the delta PM, which till now is still one of the input disturbance inputs. But later, after the modeling is done for the turbine, we'll see that, well, delta PM could also be a state variable, okay? And that would come from the turbine side. So the next class, inshallah, we will start the modeling part for the turbine. Okay, assalamu alaikum.